Hello there. Up next is determining the concentration of dissolved oxygen in our seawater. Okay, so we're using the method of a Winkler titration. Okay, back to the concepts of titration, where, the usual, we have our titrant and we'll add it to our analyte. And using some sort of indicator, we can look at the endpoint, which we can approximate to be the same as the equivalence point. In this titration, our titrant is going to be thiosulfate, which is not stable, which means we have to make a new batch of it when we want to do this reaction, which means that we have to standardize that solution that we make before we can do anything else. So let's first talk about standardization. Okay, that's just a term saying that we're determining the concentration of our titrant. Okay, so our titrant is S2O32 minus thiosulfate, and in a standardization that is unknown, which means we need to have a known analyte. If we know the concentration of our analyte, do a titration where we, the endpoint represents when titrant and analyte have reacted in equal moles, then we can determine our unknown. Okay, so our analyte is going to be I3 minus, and it will be known. Now, I3 minus, you can't just go buy a bottle of this stuff, so we're going to have to make it ourselves, and how we're going to make it is from a standard solution of potassium iodate. So our first step here is number one is to prep a solution of potassium iodate, IO3. Okay, so you're going to do that by taking some potassium iodate solid, which has been dried out, desiccated, and dissolving it in DI water to make a solution of a certain concentration. And then next, you're going to acidify the solution and add excess iodide in the form of sodium iodide. And that's going to undergo a couple of reactions, which I'll show here. So you're going to acidify and add excess iodide, I minus. Okay, so those reactions, we're taking our this iodate here, and that's going to react with the acid and iodide. So IO3 minus will react with some acid. Oops, sorry. Will react with some iodide and some acid to generate iodine and water. Okay, and this iodine can go ahead and continue reacting because it's in equilibrium since we have that excess iodide in there. It can also form triiodide, I3 minus. And that there is our analyte. It's what we were trying to titrate. Notice how this reaction gets pushed forward. Since we add acid by Le Chatelier's principle, this reaction is shifted forward, and you're making more and more I2. And the more I2 you make by Le Chatelier's, this equilibrium is shifted forward, so you're making your analyte solution. Okay, next step, number 3, we're going to add manganese chloride. Now, you'll notice right now we're just doing the standardization, which means we don't need to fix any oxygen yet. We're generating our analyte, the I3 minus, by using the standard solution, so we don't need to trap any oxygen yet. The manganese chloride, when we do our real Winkler titration, is going to be used to fix oxygen. Right now, we're not fixing any oxygen, so when you add this, no reaction is going to happen. The main reason no reaction happens is because the solution needs to be basic, in order for it to happen, and we have already acidified our solution. So why are we adding manganese chloride at all? It's just to keep the matrix the same. If we want to be able to compare our standardization titration with later our Winkler titration, we need to have similar matrices in each one. Okay, finally, we're going to go ahead and titrate. Okay, the titration reaction, we're taking that analyte, our I3- or triiodide, reacting it with our titrant, and we'll be forming iodide and a side product. Okay, triiodide is naturally yellow in color. Okay, so we're starting off yellow on our reactant side, but this iodide, I-, is clear. It's colorless. Okay, so we could do our titration and just keep adding the thiosulfate titrant until our solution changed from yellow to clear. And that, could be doable, but imagine trying to do a titration going from yellow, a very light color, to clear. It would be kind of difficult. So what you do in this procedure is to titrate as far as you can using this yellow to clear transition, but then you're going to add some starch. And when you add starch, the I3-, the triiodide, forms a complex with the starch that's it's purple or kind of black in color, but the endpoint is still clear. Okay, so now you're going from this purple, this dark color to clear, and it's much easier to see your endpoint, and hopefully you'll get a much more accurate result. Okay, also you do need to wait. You want to try to do the yellow to clear titration as far as you can before adding starch, instead of just adding the starch right away, because that starch does form the complex with the triiodide, with the analyte, and it can cause a lot to get trapped within those structures, and we want to make sure that we're able to access all of that analyte with our titrant. Okay, remember the whole point of a standardization is to calculate the concentration of the titrant. Okay, the concentration at the end, we want the units to be moles per gram. Okay, moles of S2O32- per gram of titrant. But what do we start with? At the very beginning of this, we prepared that solution of potassium iodate, so we know how many grams of that solid we use. So we're going to start over here with grams potassium iodate. And with that solid, you made a solution that had a concentration. So now we can go ahead. The concentration should have been roughly 0.01667. You should plug in the actual concentration you got. Okay, and now let's look at our stoichiometry here. So this is potassium iodate, and through this first reaction, it's a 1 to 3 reaction from the iodate to the I2, and then the I2 is in a 1-to-1 with the I3-. So we can write a stoichiometric ratio here where 1 mole of the iodate reacts with 3, or reacts to form 3 moles of the I3-. And now what about the next stoichiometric ratio? That I3- is going to react with 2 thiosulfates. So notice with this last molar ratio, we'll be left with that moles, that numerator that we're looking for of thiosulfate. So 1 mole of the I3 minus reacts with 2 moles S2O3 2 minus. Okay, if you look through, you'll need to do this conversion to convert grams to kilograms, but those can cancel out. Moles of iodate cancel out, moles of I3 minus cancel out. We have our numerator. So last thing we just need to do is divide by grams of titrant, which is the mass it took for you to reach the equivalence point, right? You are adding the S2O3 minus and S2O3 2 minus and weighed it out before and after. So just in summary, you can combine all of that analysis together into one big formula. The concentration of the S2O3 minus is equal to the mass of the iodate. Okay, so that was that very first term in my analysis there. Multiplied by the concentration. Multiplied by 6, that was all that stoichiometry. And then you'll divide by the mass of the titrant. Okay. So that's the simple version, but you're going to notice in this experiment we do what's called a reagent blank, and that we will need to take that into account in this formula. As you will see in the protocol, it's written like standard minus the mass of the titrant used for a blank titration. Okay, but this is the big formula you want to use when analyzing your standardization titrations. Don't forget error propagation. Notice that now we have both subtraction and multiplication and division happening in the same formula, so you're going to have to work through both of those error propagation formulas. Okay, but what is this term, this mass of thiosulfate used in a blank titration? Let's talk about our reagent blank. So we added all of these reagents to make this titration happen, and we need to make sure that those excess reagents are accounted for and how they may affect the titration. Okay. Okay, think about maybe those reagents are reacting with or blocking the analyte. So that would mean you would need less titrant in order to reach the endpoint that you see. Or what if those excess reagents are reacting with the titrant before the titrant gets a chance to react with the analyte? That would mean it would take more titrant for you to reach your endpoint. So what we're going to do is do a reagent blank titration in order to account for that. And what we do essentially is to do 2 titrations on the same solution back to back. Okay, so you'll add 1 gram of your standard potassium iodate solution, do it to the first endpoint, and then you'll add another gram to the same solution and titrate it again to a second endpoint. And that way you can subtract those 2 masses that it took between the 2 endpoints. Difference. Oops. Okay, and the difference between them is the reagent blank. So that this term here is the difference between the masses it took to get to each equivalence point. So I'll write that out. Mass of S2O3, 2 minus for the blank is equal to the mass that it took to get to endpoint 2 minus the mass that it took to get to endpoint 1. And notice how this could be positive or negative. Okay, depending on what way your reagents are inhibiting your reaction. Okay, so at this point, we've standardized our titrant. Now we know what concentration it is. Now that means we can go and do our real titration where we're determining the dissolved oxygen. Okay, Winkler titration. So similarly, we have our titrant and our analyte in our BOD bottle. Titrant, analyte. This time, our titrant is still SO3 2 minus, but it's known. Okay, we know the concentration of it now. Our analyte this time is still triiodide, but it's coming from our dissolved oxygen. And this is unknown. Okay, so this time we're taking our sample seawater and whatever dissolved oxygen in there, we're going to use in order to generate I3 minus. So to do that, first step is to fix the oxygen in the solution. Step 1, we're going to add manganese chloride to fix any dissolved oxygen. Okay, so that reaction is 2 manganese hydroxides react with oxygen in order to form this precipitate. Okay. Notice that this needs to occur in basic solution, so this is why we don't add acid yet. We need to, when we add the manganese chloride, we need the manganese hydroxide to form, and then this is a precipitate. So you'll add the manganese chloride and you're gonna let it sit for a while in order for it to reach all of the oxygen in the solution and precipitate out completely. Then you will acidify and add some more iodide, and that's going to help form our triiodide analyte. Okay, so we're going to take that precipitate that we just formed, react it with some of that excess iodide and our acid. That's going to form the I2 iodine, which, just like last time, can react with more of that excess iodide to form triiodide, our analyte. Okay, and lastly, we'll just titrate again with S2O3 2 minus, and that reaction is exactly the same as before. So notice how this time the analyte we're forming is dependent on how much oxygen there is in the solution. And if you go through the same stoichiometric analysis that we did in the previous problem of the standardization, you'll get a formula that looks like this, where we can calculate that concentration of oxygen you take the mass of the thiosulfate it took for the sample of seawater. Again, you need to subtract out the blank from that. And you multiply that by the concentration of the thiosulfate. And you're going to get that from part one, that original standardization. Okay, and divide by 4. If you go through the stoichiometry, that's the ratio we get here, multiplied by the volume of the sample. Okay, so notice we're dividing by volume in order to get a concentration in molarity, I believe. And that's why it becomes super useful for us to have used a BOD bottle, since the BOD bottle is made for this, of having a consistent volume measurement every time. That volume will be a constant. And you should have determined that volume of your BOD bottle back in the density and salinity experiment. Okay. As per usual, in your lab report, you should talk about some sources of error that could have occurred in this procedure. Think about fundamental flaws that are hard to avoid. I would look over the PowerPoint slides for pointers on that. We do, however, take into account a couple things, and you should discuss how well or how much an improvement these things made. So we did do a reagent blank. So maybe discuss like how much did the reagent blank help? To reduce your error. Okay, another thing, there's a formula in the protocol that helps account for any dissolved oxygen that was already present in your reagents, like in those, in the titrant, in the manganese chloride, in the acid solution. Or dissolved oxygen in reagents. Maybe talk about how large or small was that error. Did accounting for that possible dissolved oxygen in the reagents change your answer significantly or insignificantly? Okay, and of course, why do you care about dissolved oxygen? It's really important for life in the ocean or in any body of water. It's also important, your dissolved oxygen levels in your blood is important for your life as well. So this is important to think about. Okay, good luck.